Welcome and thank you for joining this review on integrating virtual reality into immersive laboratory education. In this presentation, we explore a systematic literature review that examines how VR can recreate practical lab experiences, the evidence for learning gains, and the implications for educators and institutions aiming to adopt immersive lab technologies. Here we outline the roadmap for our talk, starting with an introduction and motivation, moving through the review methodology, and then presenting results on design, learning impact, applications, and evaluation. We will end with a discussion of implications, limitations, and future directions, so you can follow how the review builds toward practical recommendations. Laboratory education has evolved from costly, risk-prone physical labs toward virtual alternatives, and this slide highlights that shift. VR offers high-fidelity, repeatable simulations that reduce safety concerns and extend access, and the accompanying image shows how simulated instruments and immersive interaction can realistically support hands-on learning experiences. Immersive learning roots itself in constructivist theory, emphasizing learning by doing and embodied interaction. Here we frame VR as an extension of those ideas, showing how multisensory experiences and manipulable virtual objects support deeper comprehension, retention, and experiential learning across scientific and technical domains. Let's summarize current research gaps and implementation challenges. Key unresolved questions include optimal immersive configurations and long-term educational effects, while practical obstacles span motion sickness, inconsistent evaluation methods, and difficulties integrating VR with existing curricula and instructional goals. Our review was motivated by the need to consolidate evidence on VR lab effectiveness and guide future work. The objectives were to assess empirical outcomes, explore diverse applications, identify implementation barriers, and provide actionable guidance to educators and policymakers to advance equitable and effective immersive laboratory experiences. The paper follows a straightforward structure to make findings easy to apply, beginning with background and objectives, then detailing the systematic methodology, presenting results on design and outcomes, discussing implications and challenges, and finally offering conclusions and future research directions to close the loop. We followed established PRISMA guidelines to ensure methodological rigor and transparent reporting, and searched a curated set of academic databases. The protocol emphasized strict selection criteria, systematic documentation, and quality assurance to produce a reliable synthesis of peer-reviewed research on VR-enabled laboratories. Our search strategy combined terms for virtual reality and immersive laboratories and focused on original empirical studies. We analyzed findings across 4 dimensions: design and development, learning performance, disciplinary applications, and evaluation challenges, to capture both technical and pedagogical aspects of immersive lab research. Inclusion criteria required empirically investigated VR laboratory environments published in peer-reviewed English journals, while exclusion rules filtered out non-empirical, AR-focused, or methodologically weak studies. This approach ensured a focused dataset that traces VR evolution while prioritizing high-quality, VR-specific research evidence. The PRISMA flowchart shows a large initial set of records that was dramatically narrowed by removing duplicates and screening for relevance. From roughly 800 identified records, we followed screening and eligibility assessments to a final set of studies, illustrating how selective criteria produced a concise evidence base for analysis. When designing immersive labs, alignment of pedagogical goals with technology and user experience is essential. Successful projects balance clear learning objectives, appropriate technological choices, interface and accessibility considerations, and strategies to overcome cost and safety constraints so that virtual labs truly support intended educational outcomes. This taxonomy categorizes immersive learning environments by application domain and design features, noting examples like embodied VR labs for engineering, mixed reality settings for collaboration, AI-enhanced systems for agricultural training, and cost-effective VR for broader STEM accessibility, illustrating how design choices reflect specific teaching needs. Different disciplines require tailored implementation approaches, from wafer preparation labs emphasizing embodied tactile procedures to mixed reality setups focused on social collaboration, AI-enhanced systems that support intelligent tutoring in agriculture, and low-cost VR solutions prioritizing accessibility for STEM contexts under resource constraints. Technical implementations vary greatly, from advanced headsets and motion controllers to smartphone-based options for broader access, and common development frameworks like Unity or Unreal are frequently used. The key design principle is clear. Technical proficiency must be tightly aligned with educational objectives and student requirements to be effective. The evidence shows that immersive technologies can improve knowledge acquisition, skill development, and learner engagement when designed appropriately. Studies report better test scores, improved procedural accuracy, and higher motivation, although the magnitude of benefits depends on context, pedagogical alignment, and evaluation methods. A comparative summary of quantitative findings highlights results such as substantially higher test scores in some STEM VR studies, reductions in cognitive load reported in science classrooms, improved conceptual understanding, and sustained motivation increases in extended XR deployments, demonstrating measurable impacts across different settings. Performance gains from VR seem driven by both cognitive and motivational processes, including spatial learning benefits, reduced cognitive load through multimodal representation, enhanced visualization of complex phenomena, greater intrinsic motivation, and increased sense of autonomy and presence that supports deeper engagement. Immersive technologies exhibit strong adaptability across disciplines with notable applications in physics experiments, engineering control and automation training, product design prototyping, and contextual learning for smart home technologies, each leveraging specific immersive features to meet domain-specific learning goals. This taxonomy links disciplinary use cases to educational benefits, showing how applications like mobile versus room-scale VR, blended virtual labs, or substitutional reality each support different learning outcomes such as spatial understanding, maintainability checks, or contextual practice in real-world scenarios. Across fields, we see recurring adaptation patterns where science and engineering focus on procedural accuracy and spatial understanding. Design-focused applications prioritize interaction fidelity and usability. And emerging domains explore novel uses where traditional instruction is lacking, emphasizing the need for discipline-specific solutions. Evaluating immersive learning requires a multidimensional framework that considers usability, learning effectiveness, and institutional adoption. Key challenges identified include motion and hardware limitations, alignment with curricular goals, assessment inconsistencies, high development costs, and institutional barriers to scaling VR initiatives. While VR demonstrates clear benefits like improved engagement, reduced cognitive load for complex concepts, and scalable practice opportunities, persistent challenges remain, including high creation and deployment costs, technological constraints, evaluation gaps, and equity concerns that must be addressed for widespread adoption. In discussing implications, we highlight theoretical support for embodied learning principles, practical guidance for educators and institutions about cost-effective deployment and teacher training, and methodological limitations, such as domain biases and underrepresentation of long-term studies that temper specific technical conclusions. In conclusion, the review finds that VR labs enhance engagement, spatial comprehension, and retention when pedagogically aligned, and that adaptable immersive technologies offer broad disciplinary utility. Future research should pursue longitudinal studies, broader disciplinary validation, equitable access strategies, and standardized evaluation frameworks to advance the field.